of the time resolved of core spectroscopy.
All right, everything looks good?
Yes.
Okay, okay. So normally when you're the last speaker of the day, you make a half-hearted apology about keeping people from the bar. But I think I'm keeping most of you from bed, I'm keeping some of you from dinner, and I'm keeping myself from breakfast. So all of that is to say that I look forward to when we can meet together in person again. So I thank the organizers for the invitation to speak. The conference title, Light Matter Interaction Theory Meets Experiment, is obviously an area that's near and dear to my heart. And so today I'm going to talk about some work that we've been doing on simulating time-resolved core spectroscopies. And so I'll start by saying what my primary interests are, and then sort of I feel like that naturally asks the question, why X-rays? Why core spectroscopy? So at heart, I am a chemist, and I am primarily interested in photo-initiated processes involving molecular excited electronic states. And so typically that will be, your excitation wavelength will be in the electron volt range. And then what I want to watch is the evolution of the nuclear and electronic character of the wave packet that prepares. And so the motion of the nuclei, the time scale for that is femtoseconds in a molecule. That's a vibrational time scale. And then the rearrangement of the electronic charge density, which right, those things taken together is our chemistry, right? The evolution of the valence electronic density with the nuclei is chemistry. The probe, typically experimentally, we probe these things, and there's lots of time-resolved spectroscopies on the market right now, transient absorption, time-resolved photoelectron spectroscopy. And typically what they have in common is that if you're interested in the evolution of the valence electronic density, you probe it directly. You probe, you ionize or you excite valence electrons to watch that evolution in real time, identically, on ideally on the femtosecond timescale. What these time-resolved core spectroscopies are proposing are to use core electrons to image the valence electronic density. And so in the case of X-ray absorption, you're using a core. So if we take this S1 state that we say is a single excitation, a homo-lumo excitation, we take this core electron and we smear it out over the pre-edge and then also into the continuum for the post-edge region of the X-ray absorption. And we use that absorption to image this electronic density. And likewise, in there, the observable will be some difference in absorbance, right? It's an absorption spectrum. Or we can choose to measure the ionized electron, and we can use this core electron, and we use the manifold of core ionized states and project those onto the valence. And we say that's how we're going to image that evolution of the valence electronic density. Now, okay, but one issue is that from a simulation point of view, computing core excited or core ionized states from initial state, we're going to need observables. We're going to need oscillator strengths, ionization cross sections. Computing core ionization or core absorption from valence excited, typically highly multi-reference, non-adiabacically coupled states, that is a difficult problem for quantum chemistry. The advent of these spectroscopies have made this a highly active area of development right now, but typically you would need a motivation to do that. And the motivation is that X-ray spectroscopy has some unique properties, right? And the primary one is that it's an atom-specific probe of electronic density, a direct probe of density, and I'm going to argue in this talk sometimes a very clear but indirect probe of the nuclear wave packet. So we take this substituted still beam here, and we come in, and we're going to come in at the oxygen K edge, which is around 500 electron volts. These are just purely calculated spectra. And we're going to say, okay, we ionize, and there's your oxygen, your main absorption feature, which would be the oxygen 1s electron into one of your unoccupied pi star orbitals. We're going to twist this nitro group. This can happen during excited state dynamics. You're going to see parametalization at this nitro group. This is going to have now a significant electronic charge. And look at that. We have a dramatic redshift in the absorption feature engendered by this charge, right? This Coulomb interaction really pushes up the energy of the 1s orbitals, which redshifts the absorption feature. And furthermore, as a bonus, we get a splitting, right? These are actually not just 1s. This is the plus and minus combination of the 1s. Due to symmetry, we now have an A prime, A double prime. We have different absorption cross sections, right? And so we get a splitting of the plus and minus combinations of the 1s orbitals. Now you can say, okay, well then let's twist this, right? This is, we see these types of things all the time in these tips, twisted intramolecular charge transfer. Let's modulate the coupling between these phenyl rings. And we're like, oh, well, this and this look sort of the same. This is not really great at imaging that. Well, shoot, just go to a different edge, right? Now we go to the nitrogen K edge and we get a totally different picture of what the dynamics are. Right here we're imaging the nitro and the amino nitrogens. And as you twist this, you create different charge environments left and right of the molecule, and you get a dramatic splitting of these two nitrogens, right? And so by changing the edge, we get different pictures of the same dynamics, right? And this is incredibly powerful. And I'm going to argue that this is an incredibly illustrative picture compared to a lot of the issues we face when we do valence spectroscopy. Okay, so the motivation is that this is potentially an incredibly illustrative view of what is what can be very complex coupled electronic and nuclear dynamics. So in this talk, I'm going to focus on the applications where theory actually did meet experiment, but all of that is possible by a lot of methodological development that I'm going to give short shrift to in this talk. So for many in the audience who we've all computed, or many of us have computed spectra of various types, and the computation of X-ray spectra is complicated by a number of things, but primarily the density of states can be very high, right? If you're computing an electronic spectrum in a molecule, as you approach the IP, the density of states can increase dramatically, but for the first couple electron volts, we are used to thinking in terms of HOMO-LUMO transitions and maybe S1, S2, S3 type dynamics, right? The manifold is not that dense. But especially as the number of cores increase, right? As the number of carbon atoms or oxygen atoms, whatever edge you're probing, the density of states can become pretty significant, right? And so if we use typical Davidson explicit or iterative diagonalization schemes, that's a lot of roots you need to compute. Furthermore, these core ionized or core excited states are extremely lifetime broadened, right? There's Auger to process, so you've created a hole at the bottom of this orbital diagram. There's going to be electronic relaxation processes that want to fill that very quickly. It's so-called Auger decay. And so you go through all this work to compute 60 to 100 sticks in a spectrum, and then you have to convolute all that effort away into some lifetime broadened envelope. And so logically, you'd say, well, let's do away with the time-independent approach of diagonalization and just compute the envelope. But the whole point of doing simulation is to sort of understand, right? We don't want to just compute the spectrum, we want to make assignments. And when you compute the envelope alone, it's hard to know, well, what are the underlying transitions? We want both, right? We want the spectrum and the assignment. So we've done a couple of different things here. A lot of the standard multi-reference electronic structure methods were simply too expensive. And so we've done a lot of work looking at using a method called Dftmrci. Grimme and others first proposed it, and a lot of work has been done by Crystal Marianne's group in Dusseldorf, and now we are sort of extending it for core spectroscopy, but also hopefully for dynamics. Long story short, you do an MRCI expansion in cone sham orbitals, for those who are not familiar. And the idea is that you get most of your dynamic correlation from the one particle expansion from the cone sham orbitals, and then that will lead to an incredibly compact MRCI expansion because we're only asking the MRCI to describe the static correlation. And so what you assume then is that any configuration that has a large energy gap, right, the things that contribute to static correlation typically are nearly degenerate. And so we introduce, among other things, this parameter that scales the Hamiltonian matrix elements as a function of delta E between them. And so we take a sparse, but fully, a Hamiltonian that looks like this, and then we make it look like this. We damp out off-diagonal elements, assuming that they're only, that differ by large energy gaps. on the assumption that they will be primarily contributing to dynamic correlation, which we've already handled from the cone-sham DFT description. And so this is how we avoid double counting dynamic correlation, and we only ask the MRC expansion to do the description of the static correlation, the multi-reference. So in this paper here, we show that the performance of this is actually quite excellent compared to other methods on the market of comparable computational expense, with the added advantage that you can describe excited states relatively easily. And we've recently, it's on the archive, it's been accepted. We're describing further advances to make this more black box, right? This is another advantage is that it's an active space method, but the active space is iteratively refined. So so unlike a CAS-PT2 or other CAS method where you define an active space, here the active space is generated automatically. And in this paper, we define ways to further black boxify that and also prune the Dftmrci wave function using ideas from selected CI so that it becomes incredibly computationally efficient. All these advances are in a GitHub repository, a generalized reference CI code that we've been developing and will serve as our development platform for this. So I don't know if I don't know if people would be well advised to use it at the moment, but in terms of scientific openness, it's there for people to look at if they are interested. Okay, so the second part are the spectral simulations, as I've said. We want to avoid doing explicit diagonalizations to compute so many roots, but at the same time, we want to be able to assign spectra. And so just very quickly, we looked at explicitly time-dependent propagation to compute these spectral envelopes, but have settled largely on a time-independent Chebyshev propagation combined with filter diagonalization. So we use the Chebyshev propagation to get the envelope, and then we use filter diagonalization to define an energy range and extract time-independent eigenstates. So one of the advantages of working in a mature field is that you don't have to reinvent the wheel. A lot of these things, these are Lego pieces that we are taking from the literature and just combining them in a new way to serve our purpose. All right. So the summary here is that a lot of these developments, what motivates them is that, as I'm about to describe, our simulation strategy is going to involve convoluting many computations of an observable, many computations of a potential energy surface, done tens of thousands of times. And so everything needs to be incredibly black box in order for this to be something that's not too onerous when you move to a new molecule. And so a lot of our effort has been on black boxifying a lot of excited state methods that are not so black box, right? Which I would put most active space methods in that descriptor. Okay. So let's get to the results. Before we get to the results, I'll give you a general strategy for how we approach these problems, whether it's for core timers of core spectroscopies or valence spectroscopies. And there are essentially three steps, right? And the first step that I think a lot of people maybe who don't work as much with experiment are forgiven for not paying as much attention to is the preparation of the initial conditions, the pump step. If you want to meet experiment, experiments always involve an initial excitation process. And typically when we simulate dynamics, maybe we'll vertically excite some distribution, or we generate initial conditions, and then we're more interested in the dynamics most of the time. But to meet experiments always involve a very specific initialization step. And sometimes that can be very difficult. And one of the examples we're going to look at, it's a real pain. But for the examples we're looking at, this excitation is going to be some short pulse in general. Sometimes perturbative, sometimes strong field, but some perturbative pulse that prepares some excited state phase-based distribution that we need to model. And then we have to propagate the wave packet on those coupled surfaces. And so for the results I'll be showing, I've used a spawning algorithm developed by Martinez and co-workers. And I use sort of canonical MRCI, typically MRCIS, and based on a CAS reference. That has been described in the literature. I'm not going to talk too much about that, other than it's a method in which it's a trajectory method in which you solve the time-dependent Schrodinger equation in a trajectory basis. But the main feature and where the spawning name comes from is that it dynamically increases as you approach regions of strong coupling between surfaces. The last step then is to somehow convolute this calculation with the calculation of the relevant cross sections for whatever observable you're interested in. And for here, the calculation of the observable, I'm going to talk exclusively about X-ray absorption. And so the relevant cross sections will be X-ray oscillator strengths between an initial state, that is some multi-reference excited valence state, and a manifold of core excited states. And this will be done for these results exclusively using CVS Dftmrci. Okay. So one of the early applications is a purely theoretical study. We are interested in ultra-fast dynamics, typically mediated by conical intersections. And we took a lot of this methodology and we simulated the X-ray absorption and X-ray photoelectron spectra of the dynamics of ethylene, which you've already seen talks on the dynamics of ethylene here in this conference. And it's sort of a prototypical molecule for modeling dynamics at a double bond and is relevant for cis-trans isomerization in polyenes. And one of the relevant motifs for relaxation is a conical intersection seam that looks like this, so-called twist pyramidalized. And it involves pyramidalization at one of the carbons, planarization at the other, and a twist about that double bond. And the key feature here is that you develop a sizable dipole across that bond. This electronic structure of this nuclear structure is characterized by a large negative charge on one side and a large positive charge on the other. X-ray spectroscopy is really good at imaging these localization of charges in molecules. And so if you can make a mapping between an electronic structure at a conical intersection and the development of a transient localization of charge, X-ray spectroscopy is a wonderful observable to use to image that. And sure enough, we predicted this splitting of nearly 5 electron volts between these two carbon 1s's. And we argue that this is potentially observable using X-ray spectroscopy. Right now, if you look at this time axis runs from minus 20 femtoseconds to 50 femtoseconds. Right? This is very, very fast. And there's not a lot. So a lot of this work is motivated by developments at X-ray free electron lasers. And they're working hard, but I don't think there's an X-ray free electron laser in the world that has this kind of time resolution with sufficient signal to noise. But they're also lab-based. So in other words, this is highly proof of concept, right? This cannot actually be measured. But there's a lot of people working on lab-based systems that potentially could get this kind of time resolution. And in fact, earlier this year, we published with a collaborator, not on ethylene, but on ethylene cation. We'd like to believe partially inspired by our previous work, where they measured exactly this, the time-resolved X-ray absorption spectrum of ethylene cation. Okay, and in the experiment, what they did was they strong field ionized ethylene to generate ethylene cation and then probed it with a carbon K-edge X-ray photon. And so from a simulation point of view, we'll get into the results in a minute. From a simulation point of view, the 3 steps that I articulated previously is the preparation is the strong field ionization to produce ethylene cation. That's the pump step. The non-adiabatic dynamics then evolve on the ethylene cation, right? And we'll do that using spawning. And the probe step is core excitation, okay? The thing that sent a chill up my spine, right, is that strong field pumps are incredibly difficult to model, right? And so simply vertically exciting the wave packet onto D0 would give you qualitatively incorrect results. And so here we actually have to, even though we mostly care about the dynamics, a lot of time went into modeling the preparation step, right? For theory to meet experiment, we had to really take time to model the preparation step. And so this is a strong field pump, 800 nanometers, 5 femtosecond full width half max, and that is even if you don't know about the units, this is an incredibly strong field. And rather than go through the details, I'll just give you the results. We use time-dependent ADC1 with a complex with an absorbing potential to model that ionization process. And there were 2 key observations that we made. First, roughly 17% of the population results in the D1, right? It actually ionizes to an excited state. You go past the D0 and you actually create both wave packets on D0 and D1. And then most importantly for the spectral simulation, it creates two different axis distributions in those electronic states, right? How the molecule is oriented in the ionizing field will influence the probability of ionization. And so when you ionize in a strong field, the D0 is primarily prepared parallel to the pump pulse, whereas the D1 is oriented perpendicular. And if your observable is X-ray absorption, where you're computing transition dipoles, having a non-isotropic axis distribution dramatically influences the X-ray absorption spectrum that you simulate. And for it to get qualitative agreement, we needed to take this axis distribution explicitly into account. Second step, we model the dynamics. So unlike in ethylene, where you have a twist parameterization, in the cation, when you prepare the D1, it's mostly a CC stretch and a CH2 scissor, right? And here we see the Ames populations, the dynamic relaxation times. We see steps in the population curve that correspond to vibrations, right? This is very much conical intersection mediated. So these transitions are localized near conical intersections. And so as you approach and depart, you see steps in the population curve. And here we see that it's mainly a compression, right, along CC. As you go to D1, you compress the CC bond, and that takes you down to the D0. So putting all this together, dynamics plus X-ray absorption cross sections plus axis distribution of the initially prepared ensemble, you get, this was incredibly encouraging, right? Before we did this, we have computed a lot of X-ray and XPS spectra prior to this study, but to get this level of agreement with experiment made us feel good that we weren't I don't know, wasting our time. And so one of the key features is that you saw two main features here, right? So these are two different absorption lines corresponding to the D0. And you see that you have this counter-phased structure. Experiment is amazing experiment. You actually see it better in the experiment than you do in the theory. But key, you have this incredibly short-lived transient feature here, just to the red of the main absorption band. And we assign that pretty conclusively to the decay of the D1, right? We see that here we take this feature, we blow it up, and we see that this is, as you compress the CC bond, this band moves to the blue, and what you're seeing here, this chirp, is actually the CC bond stretch as it decays. And we back this up with looking at the static spectra. The D0 dynamics, this are largely uncoupled, and here you see vibrational dynamics exclusively. You see this sort of counterphase vibration, which we can even assign to the two different features, right? That we have one going into the pi, and as you stretch, it goes to higher energy as you stretch it one way, whereas the other excitation is into the pi star, and that is going to have a different energy profile as you stretch, right? One will go up and the other will go down as you compress and stretch that bond. So in closing, I want to close with some very recent calculations. We actually want to use this technique to image conical intersection dynamics for the hard cases, right? In the hard cases I'm defining here is when you have multiple relaxation pathways to the ground state. Theory makes incredibly elaborate predictions about the CI looks like this, or it looks like this, and you get a branching ratio of this and that between the two. And then the experiment tends to be a blob. And then you sort of try to make a case that, well, the experiment's, confirming or denying this incredibly complex simulation I did. We're hopeful that X-ray spectroscopy can do that. So a more complex case, as we're describing here, is 1,3-butadiene, where you have in the valence region two nearly degenerate states, a bright state and a dark state, right? Singly excited, characterized by doubly or multiply excited dark AG state. And as you excite primarily to the B, this thing undergoes bond alternation, stretches, it starts to twist, and you get a mixing. As you do that, you get a mixing of these A and B characters. And as you come out the other side, you essentially have two different, simulation predicts, you get two different relaxation motifs. You get sort of a cis-trans like CI seam that results in relaxation to the ground state. And you also get something that looks like more ethylenic, where you have sort of parameterization at either a terminal or a medial carbon, right? You get essentially a localization of the dynamics at a double bond. And depending on your potentials, depending on how you describe the initial conditions, you'll say it's mainly this and a little bit of that, or a little bit mainly this and a little bit of that, right? It's very sensitive to your potentials. It's just sensitive to your initial conditions. And so the time scale, here we implicitly modeled pumping at 200 nanometers. And this is the time scale. We prepare primarily bright state that decays to some mixed character, S1, and then the rise time of the ground state's on the order of 200 femtoseconds. Now, this characterizing the dynamics is very difficult. We've written many papers on this, and trying to say something coherent about the dynamics, a coherent story, is difficult. If you look primarily at the nuclear geometries, right, we have a real mixing of characters. We have found that looking primarily at the electronic components is actually more illustrative. And here what we're plotting is we're plotting the differential charge across this terminal bond, and we're saying that these two paths can be distinguished by the electronic character, right? This is going to have a large dipole across this terminal bond, whereas this, not so much, right? This is the transoid. This is a sort of a radicaloid structure. You have a lot of unpaired electrons along this backbone, whereas here we have a sizable negative charge. And if we take all our trajectories from the simulation and we compute this delta Q, how to compute charges in electronic states is another topic. We use iterative Hirschfeld. We've done a lot of looking at how best to do this. And here the branching between the two paths is very clear, right? We have essentially a whole bunch of these dots are the spots. So the overall heat map is all trajectories at all times. And the spawn points, which we correspond to transitions to the ground state, are given by dots. And we're calling these dots the transoid structures, and these dots the twist param structures. And you see this bifurcation more clearly via this analysis than a lot of other things I've looked at. Over here, we have these black dots, and they correspond to parameterization at a medial carbon. And you can see, so you see all these different types nicely split out from each other. And in fact, if you take an average Cartesian structure of these red dots and superimpose it on the transoid Mecke, it's amazing, right? They're the same thing. Okay. I should speed up a little bit here. So before I get to my final results, we have looked at this using valence spectroscopies, right? The dynamics are the same whether you probe with a UV photon or an X-ray photon. And again, in these previous pair papers, we looked at valence photoelectron spectroscopy. And this was an incredible experiment where they measured the electrons in the photofragments in coincidence and can split out the parent ion, which they assigned to S2, to the dissociated ion, which they assigned to S1. And this is the result, right? The simulation agrees very well with experiment. That's gratifying. But the S1 signal is just this broad delocalized thing. And if you try to say this part of this broad delocalized thing is this structure, and this part of this broad delocalized thing is that structure, you are not successful. It's very hard. The theory predicts a branching between those motifs that the experiment cannot resolve, all right? Because it's sort of broad in nuclear space, this thing's sort of broadly delocalized. So this is our simulation of the time resolved X-ray absorption spectrum for butadiene using those same dynamics. And again, we split out the S2 contribution, which is primarily the bright pi star, the S1 contribution, which is mixed, and the S0 contribution, which is largely hot, vibrationally hot ground state. And so here's the S2. So here's a static spectrum. This is this is an X-ray absorption spectrum computed at the S0 minimum from the bright pi star. And we can assign this feature right here to this feature right here. And likewise, here's the ground state at the ground state minimum. Again, we have a feature here and a feature here, which very clearly map to here. But as we said before, all the actions on S1, can we resolve our different decay channels from the S1, okay? And we sort of say, yeah, maybe, right? A nice thing about being in this field is that these experiments are on the verge of being done. And so theory can actually lead experiment in this case. And here we actually can resolve. We have a transoid, so this is the X-ray absorption from the transoid Mecke. And we see it's the green line that we care about. And this is that feature there. And then we see a blue shift for the twist pi that is, you know, maybe an EV shifted relative to the transoid structure. And so, yeah, that much more so than the valence spectroscopy, we can actually resolve two different peaks. And furthermore, this peak at high energy here which corresponds to this feature, would almost be a fingerprint of these twisted parameterized structures. Furthermore, we have shown that isotopic methyl chemical substitution can really affect the branching ratio between these two things, right? And so we now have a mechanism to compare theory and experiment across a whole bunch of variables and say, okay, are the predictions of theory holding up to experimental scrutiny? Okay, so in conclusion, I hope I've shown that X-ray spectroscopies are incredibly sensitive to transient electron structures associated with passage through a conical intersection. We have a highly successful proof of concept on ethylene cation showing that we can simulate these things to near semi-quantitative accuracy. And our hope is that we can motivate experiments to look into more complex examples that predict a branching between different electronic relaxation pathways. So this work was done at the NRC in New Ottawa. The real leaders on this are a postdoc in my group, Asaka Seydu, and Simon Neville, who's now staff scientist at the NRC. I'd also like to highlight the contribution of my long-term collaborator, Albert Stolo, who is setting up a lab at U Ottawa to hopefully do some of these experiments. And with that, I thank you for your attention.
Thank you very much. Thank you very much for nice presentation. Any questions? Everybody? No? Okay, okay. Professor Massimo?
Okay, so, Michael, that's one example, the butadiene that is very close to my heart. And I think that the work you have done is just about fantastic. I mean, we have always been talking about these two different types of conical intersections. And at one stage, we thought that CAS-SCF was biasing the calculation towards the kind of diradical that you have a conical intersection. And then, of course, we knew that it could also become kind of a charge separation type of conical intersection, and now you turned out with this simulation, and you have clearly seen that are actually two different pathways going, basically in parallel. So this raises the question about the energetics. Are they really kind of the general pathway? Can you actually quantitatively tell us which one is the most important? And on top of that, the multi-reference CI DFT that you are using, do you really think is accurate enough to really reproduce this competing, this channel competition correctly? Of course, I know that you hope to have the experiment, but if I have well understood that the experiment is not there yet, not completely there yet. Please comment on this.
Yeah, so there's a couple things to comment. So the first thing, the idea that there's a single branching between those pathways, I think, is not true. It depends, given the dynamics, it depends how you prepare it. What are your initial conditions? It's incredibly ballistic. And so if you pump at 216, or you pump at 200 nanometers, so 6.2 or 6 or whatever, you'll get different branching, different results. And so the question of whether your potentials are accurate enough